Point at the ceiling. Go on. Wherever you are, put a finger up and hold it there. You have just pointed at the most expensive direction in physics. Every planet, every moon, every spacecraft ever launched is riding inside a flat disk about 30 times wider than it is thick, and somewhere near where your finger is aimed is the one heading nothing has ever travelled. There is nothing in the way. No wall, no barrier, no debris. Empty space, cleaner than the space we fly through every day. And in 65 years of spaceflight, exactly one machine has ever been built to go that way. It could not get there on its own. It had to ask Jupiter for a favour, and it still fell 10 degrees short. Turning to face the way you are pointing costs about 3.5 times more than leaving the solar system altogether. By the end of tonight, you will know exactly why it is impossible to escape the solar system, and it has nothing to do with distance. Get comfortable. If you're the kind of person who enjoys watching a simple question turn out to have a far stranger answer than anyone promised, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word up will not mean what it did this morning. Now, let's slowly settle in. Nothing is holding you up. Nothing ever has. The floor beneath you is not pushing you into a direction called down. It is simply the last solid thing between you and the centre of a planet you have been falling toward, without interruption, since the moment you were born. And yet you have never once been confused about which way is up. You know it right now, without looking, without thinking, the way you know your own name. That certainty is the most reliable feeling a human being has, and it is also the most local. It does not travel. It cannot be packed. The instant you leave the surface of this particular world, it stops working, and what replaces it is not a different up but no up at all. A directionlessness so complete that the human nervous system has to be talked into accepting it, slowly, over the course of about 3 days. Consider how thoroughly your body is committed to the idea. You're not detecting up with one sense. You're detecting it with at least 3, and they normally agree with each other so completely that you have never noticed them as separate things. The first lives inside your inner ear, in a set of fluid-filled chambers called the vestibular system. Tiny hair cells sit in a gel loaded with calcium carbonate crystals, and when your head tilts, that weighted gel sags in whatever direction gravity is pulling, and the hair cells report the sag. That is your inner ear telling you, continuously and without any effort on your part, where down is. The second system is your eyes. They are not measuring gravity at all. They are reading the room, the horizon, the line where the wall meets the floor, the orientation of a doorway, the direction the letters on a page are pointing. Your visual system takes all of that and produces its own independent estimate of which way the world is stacked. The third system is spread across your entire body. Pressure receptors in the soles of your feet, in your knees and hips, in the muscles of your back and neck, quietly report where weight is pressing. Sit down and your body registers a change in the map. Lie down and it registers another. This is proprioception, and it is running constantly, silently, in the background of every moment you have ever been awake. On Earth, these 3 systems always agree. Your feet feel pressure downward, your eyes see a floor below and a ceiling above. Your inner ear detects a steady pull in the same direction. 3 separate biological instruments, evolved over hundreds of millions of years, all returning the same answer all the time. Your brain fuses them into a single, seamless, unquestioned certainty, and then it hides the machinery from you entirely. You do not experience 3 signals being reconciled. You experience a floor. Now take that body and put it in orbit. You wake in a module with no floor. There is a surface below you in the sense that it is nearer your feet than your head, and someone has painted it, and there are handrails running along it, and the labels on the equipment are oriented as though it matters. Your eyes accept this. Your eyes are the only part of you still doing its job. Your inner ear reports nothing. The gel is not sagging. The crystals sit exactly where they are, and the hair cells have no direction to give you. Your feet press against nothing at all. The pressure receptors that have been reporting your weight against a surface every single second of your life have gone quiet for the first time, and they have no vocabulary for what to say instead. So you take the painted surface at its word. You decide that is down, because something has to be, and for a few hours it holds. You move along the module head up the way you have always moved, and it almost feels normal. Then you push off gently and drift through a hatch into the next module, where the equipment is mounted the other way around and the labels run in a different direction, and the entire universe rotates 90 degrees without anything having moved at all. There is no falling sensation, there is no alarm, nothing lurches. The room you just left is still exactly where it was. What has changed is that your brain has quietly reassigned which way the world goes, in the space of about 2 seconds, on the basis of paint. That is all it took. 2 systems have gone silent, the third one is guessing, and up turns out to be whatever the guess says it is. Astronauts describe this adjustment, and the word most of them reach for is not fear, it is nausea. Roughly half of everyone who has ever gone to orbit experiences some degree of what is called space adaptation syndrome in the first 2 or 3 days, and it is not caused by motion. It is caused by disagreement, by an inner ear insisting there is no down, and a pair of eyes insisting there is, with no way to reconcile them. Motion sickness on Earth works the same way in reverse. You feel ill in the back seat of a car because your inner ear reports movement your eyes cannot see. The adaptation, when it comes, is a demotion. The brain stops trusting the inner ear and hands the whole job to vision. It works so well that astronauts returning after long missions often have the opposite problem, a period of dizziness and unsteadiness on the ground while the inner ear relearns how to matter. There is a detail in station design that gives the game away entirely. The modules of a large orbital station do not have a floor and a ceiling in any physical sense. They have a working orientation, chosen by engineers and agreed on by the crew, so that everyone has something consistent to hold on to. It is a convention, in the same category as deciding which side of the road to drive on. You could take the entire station and turn it upside down relative to the Earth, and nothing whatsoever would change for the people inside. No one would fall, no one would need to correct anything, nobody would feel a thing. The only reason there is an up in that station at all is that a group of people on the ground decided years earlier which way to mount the lockers. It is worth being precise about why any of this happens, because the usual explanation is wrong. People say there is no gravity in orbit. There is a great deal of gravity in orbit. At the altitude of a space station, roughly 400 kilometers up, the Earth's gravitational pull is still about 90% of what it is at the surface. If you could build a tower that tall and stand on top of it, you would weigh very nearly what you weigh now. What a station does is fall. It is moving sideways at about 7.8 kilometers per second, fast enough that as it falls toward the Earth curves away underneath it at the same rate. It never gets any closer, it never gets any further, it simply falls forever in a circle, and everything inside it is falling at exactly the same rate, which means nothing inside it presses against anything else, which means weight, the sensation, not the force, disappears completely. You do not float because gravity is stopped. You float because you and the wall are falling together and neither of you can tell. None of this is a quirk of astronauts. It is a clue, and it is the most important clue in this entire subject. 3 independent systems tuned by hundreds of millions of years of evolution produced a certainty so total that no human being in history questioned it, and all 3 of them were tuned for exactly one condition: standing on a large gravitating body with a steady pull in a single direction. Remove that one condition, and the certainty does not become harder to work out. It stops existing. Up and down do not become difficult to distinguish from other directions. They stop being different from other directions at all. Take that idea and hold it, because it is the first crack in something you have believed your whole life. Your sense of up was never a property of space. It was a property of gravity. Specifically, the gravity of whichever large body happened to be closest and strongest. On Earth, up points away from Earth. Standing on the Moon, up points away from the Moon, and the Earth hangs in the sky at a fixed spot, neither rising nor setting, in a direction that is neither up nor down but simply over there. Near Jupiter, up would point away from Jupiter. There is no universal ceiling. There is no cosmic floor. Every up you have ever trusted was on loan from whatever mass happened to be nearest. Every up is borrowed. Hold on to that phrase because it is going to come back later, with considerably more weight attached to it than it has right now. And this is where the question that brought you here begins to change shape. If you asked most people why we have never simply flown straight up and out of the solar system, they would picture something like a ceiling, a boundary, a belt of radiation, a wall of debris, some obstacle at the top of the sky that has to be got past. There is no such thing. There is no top of the sky. Above and below the plane where all the planets orbit, space is not merely passable, It is emptier and cleaner than the space we routinely fly through. But the moment you accept that up is not a fixed direction, the question stops being about obstacles and becomes something harder. If up is only ever defined by whatever gravity is nearby, then out here, orbiting a star with the Earth beneath you and the Sun 93 million miles away, what would up even mean? What direction would you point at, and what exactly would you be leaving? By the end of tonight, you will know precisely what that direction is, precisely what it costs, and precisely why not one object built by human hands has ever travelled in it. But the answer starts with the shape, the actual shape of the solar system, which is almost certainly not the shape you are picturing. Find a picture of the solar system. Any picture will do. The poster on a classroom wall, the illustration at the front of an old encyclopedia, the image that appears when you search for it. Almost all of them make the same mistake, and almost all of them make it in the same direction. They show the Sun in the middle and the planets arranged around it, and to fit 8 orbits onto a rectangular page without the lines overlapping, the artist tilts them. One orbit leans this way, another leans that way, and the result is a picture that suggests the planets are scattered around the Sun the way bees are scattered around a hive, in every direction, at every angle, filling a rough sphere of space with the Sun somewhere near its centre. That picture is wrong, and it is not wrong by a little. The real solar system is close to flat. Not approximately flat, not flat if you squint. Flat in a way that would be difficult to achieve on purpose. Earth's orbit around the Sun defines a surface, and astronomers call that surface the ecliptic. It is the reference plane against which almost everything else in the solar system is measured, and the numbers are worth hearing one after another, because the list itself makes the point better than any description could. Mercury's orbit is tilted 7.0 degrees from the ecliptic, and Mercury is the outlier, the most steeply inclined major planet in the system. Venus is tilted 3.4 degrees, Mars 1.8, Jupiter 1.3, Saturn 2.5, Uranus 0.77, Neptune 1.8. That is the whole list. 8 planets, spread across 4.5 billion kilometers of space, and the largest disagreement between any of them in the plane of Earth's orbit is 7 degrees. Most of them are within 2. To put a shape on that, take Neptune's orbit as the outer edge, about 30 times the distance from the Earth to the Sun, call it 4.5 billion kilometers in radius. Across that entire span, the vertical spread of the major planets above and below the mean plane is on the order of 1 Earth-Sun distance. That is a ratio of roughly 30 to 1, width to thickness. Shrink the whole system down until it is 28 centimeters across, the size of a large dinner plate, and the planets would occupy a layer about a centimeter thick. The comparison is not a metaphor. The proportions are the proportions of a plate. There is another way to feel it. Imagine drawing the solar system accurately on a single sheet of paper, with Neptune's orbit reaching the edges. At that scale, the vertical thickness of the whole planetary system, the full spread of every world above and below the mean plane, would be about the width of your thumb. Everything else, the entire remaining volume of the sphere that most illustrations imply, is empty. It is not that the planets happen to be arranged in a layer. It is that the layer is the solar system, and the sphere around it is a drawing convention. And you're not looking at that plate from outside. You're inside it. You're a passenger on one of the objects embedded in it, moving along with it, which is why the shape is so easy to miss. The same way it is difficult to see the shape of a lake while swimming in one. You're not on the disk. You're in it. There is a second plane, and it matters more than the ecliptic, even though almost nobody has heard of it. The ecliptic is defined by Earth, which is a small rocky planet with very little say in anything. The invariable plane is defined by the total angular momentum of the entire solar system. Every planet, every moon, every significant body, weighted by mass and speed and distance and added together. It sits about 1.5 degrees away from the ecliptic, and it barely shifts over millions of years, because angular momentum is one of the quantities physics refuses to destroy. If you want to know what the solar system actually thinks its own plane is, the invariable plane is the answer, and it is dominated by one object. Jupiter alone carries something like 60% of the orbital angular momentum in the entire system. The invariable plane is, to a very good approximation, Jupiter's plane, and every other body in the solar system is orbiting in a surface that a single planet is mostly responsible for defining. Keep that in mind. It will matter a great deal later, in a way that has nothing to do with geometry and everything to do with fuel. nearly everything of any consequence respects this layer. The main asteroid belt between Mars and Jupiter is concentrated within a few degrees of it, hundreds of thousands of catalogued bodies, all riding in the same thin sheet. Jupiter's Trojan swarms, the two enormous clouds of asteroids trapped 60 degrees ahead of and behind the planet in its orbit, share Jupiter's plane closely enough to be part of the same structure. Short-period comets, the ones that return on schedules measured in decades, come from the Kuiper belt and arrive on paths that hug the ecliptic. The ring systems of Jupiter, Saturn, Uranus, and Neptune each sit in the equatorial plane of their own planet, and those equators are themselves broadly aligned with the system as a whole. Saturn's rings deserve a sentence here on their own, because they are the clearest demonstration anywhere in the solar system of what flat actually means. The ring system is about 280,000 kilometers across, wide enough to stretch most of the way from the Earth to the Moon, and in most places it is thought to be no more than about 10 meters thick. 10 meters. If you scaled the rings down to the width of a football pitch, they would be thinner than a sheet of cling film. That is what a structure looks like when rotation and collisions have been given a few 100 million years to flatten it, and it is a miniature of the process that produced everything else. The pattern holds so consistently that it is easier to list the exceptions. Pluto is inclined 17 degrees, which is a genuine outlier and a signature of a violent history involving Neptune. The dwarf planet Eris is inclined 44 degrees and spends most of its enormous orbit well above or below the plane the major planets are so careful about. Sedna is at nearly 12 degrees, but travels so far out that even a modest angle carries it an extraordinary distance from the sheet. Each of these is a hint that the flatness has an outer limit, and we will come back to where that limit is. Here is the part that ought to make the hair on your arm stand up slightly. Human beings have been looking directly at this structure for as long as there have been human beings, and for almost all of that time nobody understood what they were seeing. Ancient sky watchers, in every culture that kept records, noticed that the sun, the moon, and the 5 visible planets never wandered freely across the sky. They moved along a narrow band, night after night, year after year, returning to the same strip of constellations. That band is called the zodiac, and entire calendar systems, navigational methods and mythologies were constructed around it. Nobody could explain why those particular objects were confined to that particular strip, while the stars filled the whole sky. The answer was sitting in plain view, and could not possibly have been guessed. They were looking edge-on at a flat disk from a vantage point inside it. The zodiac is not a band of sky. It is the solar system, seen along its own thin edge. So now the question that opened tonight has a precise meaning for the first time. If the solar system is a flat disk, then up is not vague and not local, and not a matter of opinion. Up means perpendicular to that disk, straight out of the plane, either above it or below it, away from where every planet, every moon, every asteroid, and nearly every comet is lined up. Astronomers have even given the two directions names and coordinates. The north ecliptic pole sits in the constellation Draco in the northern sky. The south ecliptic pole sits in Dorado in the southern. There is a pole in the sky with no star in it, no bright marker, no ancient name, nothing anyone ever steered a ship by. Remember that. It will mean something entirely different by the end of tonight. It is worth noting who does look in that direction, because it is not spacecraft. It is telescopes. The planet-hunting observatory called TESS deliberately stares at the two ecliptic poles for its longest continuous observations, for a reason that is a small joke at the expense of this entire subject. Those two patches of sky are the only ones that are never blocked by the sun over the course of a year. Everywhere else on the celestial sphere gets swept behind our own star at some point in the orbit. The ecliptic poles never do. They are permanently, conveniently visible, and permanently, inconveniently unreachable. And there is nothing in the way. That is the strange part. There is no wall above the ecliptic, no debris field, no radiation barrier, no obstacle of any kind. Space above and below the plane is emptier and cleaner than the space we routinely fly spacecraft through. It is, if anything, easier country. And yet, in more than 65 years of spaceflight, after every planet has been visited, after landers on Mars and Venus and Titan, after 5 spacecraft on trajectories that will carry them into interstellar space, exactly one mission has ever been built for the purpose of going up. One, and it could not get there on its own. Before we can understand why, we have to understand where the disk came from in the first place, because the reason it is so expensive to leave is written into the reason it exists at all. The flatness is not a coincidence, and it is not a design. It is a scar. Something happened 4.5 billion years ago that removed every possible alternative shape, and the solar system has been living inside the result ever since, unable to remember any other way of being arranged. Start with what was here before anything else was. There was a cloud, gas and dust, mostly hydrogen and helium, with a scattering of heavier elements donated by earlier generations of stars that had already lived and died. It was roughly spherical, it was enormously larger than the solar system is today, and it was rotating. Not quickly. Not in any way that would have been obvious to an observer. Just slowly, imperceptibly, the way almost everything in the universe rotates a little, because nothing ever forms perfectly still. That slow rotation was the entire story. Everything that follows is a consequence of it. Angular momentum is one of a small handful of quantities that nature genuinely refuses to destroy. You can move it around, you can transfer it from one object to another, you can redistribute it, concentrate it, spread it out. What you cannot do, under any circumstances anyone has ever observed, is get rid of it. In a closed system, the total stays exactly the same, forever. So when gravity began pulling that cloud inward, and it did, because a cloud that large cannot hold itself up against its own weight, the rotation could not simply be left behind. The same total amount of spin had to fit inside a very much smaller volume, and the only way for that to happen is for the spin to get faster. You have watched this happen. A figure skater spinning with her arms extended pulls them in against her chest, and without pushing against anything, without adding any energy, she accelerates into a blur. She has not created rotation. She has concentrated it. The collapsing cloud did exactly the same thing, over a span of perhaps 100,000 years, and by the end of it, a region of spacelight years across had become a whirling structure, turning fast enough to matter. But faster spinning does not by itself flatten anything. A spinning ball is still a ball. If rotation were the only ingredient, the solar system would have ended up as a smaller, faster-turning sphere of gas, with planets scattered through it in every direction, which is incidentally exactly the picture those classroom posters accidentally show. What flattens a cloud is collisions. Inside that collapsing cloud, the density was rising steadily, and the particles of gas and dust were not all moving the same way. Some were travelling along the direction of the bulk rotation. Some were moving against it. Enormous numbers of them were moving up and down, above and below what would eventually become the plane, on paths tilted at every conceivable angle. And they were running into each other constantly. Every collision averages out the motion of the two things that collided. That is all a collision does. Now consider what that means statistically. A particle moving along with the general rotation collides with another particle moving along with the general rotation, and both of them come out still moving along with the general rotation. The motion is reinforced because nearly everything else in the cloud shares it. But a particle moving perpendicular to the rotation, drifting upward out of the eventual plane, meets another particle drifting downward into it, and the two of them cancel. There is nothing to reinforce vertical motion. There is no consensus behind it. Collision by collision, grain by grain, over thousands of years, the up and down motion in that cloud was simply subtracted, and it did not vanish. Energy never does. The vertical motion was converted into heat, and the heat was radiated away into space as infrared light. This is not a theoretical claim. It is why young star systems still in the process of forming glow so brightly in the infrared. You are watching them shed the energy of their own vertical motion in real time as they flatten. That is the sentence to hold on to. The solar system is flat because 4.5 billion years ago, every particle that tried to go up was cancelled out by a particle going down, and the difference was thrown away as heat. Think about what that leaves behind. The disk is not a shape that the planets chose. It is not a structure anyone or anything selected. It is the residue. The only motion that was left standing after every alternative had been erased, one collision at a time, in the dark, before the Earth existed. Every planet in this system condensed out of material that had already been flattened before there were any planets. Their orbits inherited the orientation of the disk, the way a child inherits handwriting from years of copying the same motion, not because it was chosen, but because the environment they formed in offered nothing else to copy. and you are sitting inside that residue right now, on a rock that is still executing the only instruction it ever received. The idea itself is much older than the evidence for it. In 1755, Immanuel Kant, better known for philosophy than for astronomy, proposed that the solar system had condensed out of a rotating cloud. 40 years later, in 1796, Pierre-Simon Laplace worked the idea into a more rigorous form, and for most of the 19th century it was the leading account of where the planets came from. Then it fell out of favour, and the specific thing that killed it was the angular momentum problem we're about to come back to. Nobody could explain why the sun spins so slowly. The nebula hypothesis spent decades in the wilderness before 20th century astrophysics rescued it. It took another 100 years and a radio telescope in a desert to actually photograph one. We have confirmed the process from the outside. In November of 2014, the ALMA Radio Observatory in the Atacama Desert released an image of a young star called HL Tauri, about 450 light-years away. It showed a disk of gas and dust, geometrically flat and startlingly bright, with sharp concentric gaps carved into it. The early footprints of planets sweeping their own orbits clear. It was the first time anyone had seen the process this clearly, and dozens of similar disks have been imaged since. Typical protoplanetary disks are measured to have thicknesses of a few % of their radius, which is the proportion of a sheet of paper the size of a football pitch. Flat rotating disks are not a quirk of our particular corner of the galaxy. They are the ordinary outcome whenever a rotating cloud of gas collapses under its own weight. The small differences between our planets tell their own story. Mercury's 7-degree tilt, the largest in the system, is generally attributed to the chaotic collision-heavy region nearest the Sun, where there were fewer large neighbouring bodies to smooth out residual irregularities. The gas giants are the flattest of all, Uranus at less than a degree, Jupiter at 1.3, most likely because they built themselves by gathering enormous volumes of gas from the smoothest, most thoroughly settled layer of the disk, the part where the collisional ironing had already finished its work. There is one more thing worth flagging now because it becomes important much later. The flatness has an outer limit. Computer models of the early solar system, the family of simulations usually called the NICE model, suggest that the giant planets moved substantially after they formed, and in doing so they gravitationally flung enormous numbers of small icy bodies outward in every direction. Out at the edge of the Sun's territory, those scattered objects are believed to form a roughly spherical shell rather than a disk, because out there, encounters are so rare that nothing ever cancelled their vertical motion, a flat inner system surrounded by a spherical outer one. The ironing only reached so far, and there are 2 loose threads in this account that honesty requires mentioning, because they are still open. The first is that the Sun holds 99.86% of all the mass in the solar system, and only somewhere around 2% of its angular momentum. Jupiter, a body about 1,000th the mass of the Sun, carries more rotational momentum than the star does. That is not a small discrepancy, and it has had a name in the scientific literature for more than a century. The leading explanation is magnetic braking. The young Sun's magnetic field lines threaded the ionized inner disk and acted like a lever arm, dragging on the star's rotation and flinging momentum outward into the surrounding material. The mechanism is plausible and broadly accepted. The details are still argued about. The second loose thread is stranger. The Sun's own equator is tilted about 7 degrees to the ecliptic. If the Sun and the planets condensed out of the same rotating disk, the Sun's spin axis ought to be perpendicular to that disk. It is not. Nobody knows why. Proposals include a passing star that torqued the young system, an asymmetry in the original collapse, and a distant, undiscovered massive body pulling on the plane over billions of years. The disk that defines every direction in this solar system does not quite line up with the star at its centre, and after 400 years of astronomy, we still cannot say what tilted it. So the plane exists. We know how it got there, more or less. We know it is a memory of rotation that nothing since has had enough energy to erase. The question is, what happens when something built by human beings tries to erase it anyway? And to understand that, you need to know how fast you're already moving. There is a number that almost nobody has ever heard, and it explains more about spaceflight than any other single figure. It is 29.8 kilometers per second. That is how fast the Earth is moving around the Sun. In more familiar units, it comes to roughly 107,000 kilometers per hour, or about 66,600 miles per hour, or 18.5 miles in every second. not 18.5 miles per minute, per second. In the time it takes you to say the number out loud, you have moved further than most people travel to work. You're doing it right now. Sitting still, lying down, half asleep, you are travelling faster, by a very wide margin, than any vehicle you have ever ridden in a direction you have never once thought about, and you cannot feel a thing. There is nothing to feel. Everything around you is moving at the same speed, so there is no relative motion to detect, no wind, no pressure, no sense of being carried. It is the most consequential fact about your physical situation, and it is completely invisible. The speed is not quite constant, because Earth's orbit is not a perfect circle. At the beginning of January, when the Earth is closest to the Sun, we are moving at about 30.3 kilometers per second. At the beginning of July, at our furthest, we slow to about 29.3. Over the course of a year, you speed up and slow down by a kilometer per second, and you have never once noticed. It is worth stacking the motions you are carrying because the orbital one is only the second largest. The Earth's rotation moves you at about 0.46 kilometers per second at the equator. The orbit around the Sun moves you at 29.8. The Sun's own orbit around the center of the galaxy carries the whole solar system at roughly 220 kilometers per second. And relative to the cosmic microwave background, the oldest light in the universe, the closest thing there is to a universal reference, we're moving at about 370. Only one of those numbers matters for spaceflight, and it is the small one. The galactic motion is irrelevant because everything nearby shares it. The Sun, the planets, the nearest stars, all of it is being carried along together, so there is nothing to fight and nothing to gain. The orbital velocity is different. Within the solar system, that 29.8 kilometers per second is the difference between where you are and where you want to be, and it is the only inherited motion you would ever have to cancel. Now consider a rocket standing on a launch pad in Florida. That rocket is not stationary. Nothing about it is stationary. Before its engines have lit, before any human being has made any decision about where it is going, it is already moving around the Sun at 29.8 kilometers per second, because it is bolted to a planet, that is. When it clears the atmosphere, it takes that motion with it, every gram of it. There is no opting out, no way to leave the inherited velocity behind on the ground, no maneuver that begins from rest. Every object that has ever been launched from the surface of the Earth began its life in space already travelling at 18.5 miles per second, sideways, in the plane of the disk. If your destination is another planet, that inherited speed is the single greatest gift in the entire enterprise. It is free velocity, delivered before you started, in exactly the direction that is useful. Launch in the direction of Earth's own motion, and you get a running start toward the outer solar system. Launch against it, and you begin falling inward. Nearly every efficiency trick in interplanetary navigation, transfer orbits, launch windows, gravity assists, the whole architecture of how missions are planned, is a method for spending Earth's inherited velocity rather than fighting it. For comparison, notice how small the other freebies are. The Earth's rotation, the spin that carries you from night into morning, contributes only about 0.46 kilometers per second at the equator. That is why launch sites near the equator are considered valuable. It is a real bonus, and mission planners fight for it. But it is a 64th of the orbital velocity. The rotation you can feel in a sunrise is a rounding error next to the motion you cannot feel at all. You can see the inherited velocity governing missions in the most mundane way imaginable, the calendar. Launches to Mars happen in windows roughly every 26 months, and outside those windows they simply do not happen, no matter how ready the spacecraft is or how much anyone wants to go. The window exists because a transfer to Mars is not a journey from here to there. It is a decision to add a specific amount of speed to the motion you already have, at a specific moment, so that the ellipse you fall into happens to intersect Mars when Mars gets there. You are not steering toward a planet. You are adjusting an orbit you are already in and waiting for geometry to do the rest. Every interplanetary mission ever flown has worked this way, and every one of them was built on top of the velocity Earth handed it for free. If your destination is out of the plane, everything reverses. That same inherited speed stops being an asset and becomes the largest obstacle in physics. Here is the specific reason, and it is the hinge of this entire subject. Going up does not mean adding an upward push to a spacecraft. It means cancelling a sideways one first. As long as you are still carrying 29.8 kilometers per second of motion along the plane, Any upward push you apply simply tilts your path by a small angle. You're not climbing out of the disk, you're travelling around it at slight incline. To make upward the dominant direction of travel, to actually go up rather than merely leaning, you have to get rid of nearly all of the sideways motion you were born with, and getting rid of motion costs exactly as much as creating it. Stand on a merry-go-round. Not a gentle one turning fast enough that you have to hold on. Feel it in your arms and in the soles of your feet, that steady outward pull, the ground beyond the rim smeared into a blur that comes around again and again. Now someone gives you an instruction. Walk straight off the edge, not tangentially, not at an angle, directly away from the centre, along a perfectly straight line, with no sideways drift at all. You try to work out how, and you find that there is no how. You cannot simply step off. Your body's already going around, and the instant you leave the platform you will keep going around, flying off in whatever direction you happen to be facing at that moment, carrying every bit of your circular motion with you. The straight line you were asked for does not exist as an option. To leave along a true radial path you would first have to shed the rotation you already have, all of it, and only then start walking. And the faster the platform turns, the more of yourself you have to spend doing it. Now scale the merry-go-round up. Its radius is 150 million kilometers. Its rim speed is 29.8 kilometers per second. You have been standing on it your entire life without noticing it turn, and the instruction, walk straight off the edge, is precisely, exactly, the instruction that every mission planner in the history of spaceflight has looked at and quietly declined. To talk about this properly, you need the unit that spaceflight actually runs on, and it is not distance. Distance in space is nearly free. Once you're moving, you keep moving. Empty space charges nothing for being crossed. What costs is changes of motion, and the unit for that is delta V. The total change in velocity a spacecraft's engines must supply over the course of its mission, measured in kilometers per second and budgeted the way an expedition budgets food. Delta V is the real currency, and it is brutally exponentially expensive. The reason is the rocket equation, worked out by a nearly deaf Russian schoolteacher in the 1890s and unchanged since. Fuel does not scale with the velocity change you want. The required mass scales with the exponential of it. A chemical rocket engine throws its exhaust out at roughly 4.4 kilometers per second. To achieve a velocity change equal to its exhaust speed, a rocket must be about 2/3 propellant. To achieve twice that, about 9/10. To achieve 10 times that, the numbers stop being engineering and start being arithmetic jokes, a mass ratio in the tens of thousands to 1, meaning tens of thousands of tons of fuel for every ton of spacecraft. This is the reason rockets look the way they do. A launch vehicle is not a vehicle with fuel in it. It is a tank of fuel with a small amount of vehicle bolted to the top. The Saturn V that carried astronauts to the moon weighed about 2,900 tons on the pad, and the part that came home weighed about 5. Staging exists for exactly this reason. You throw away the empty tanks as you go, because carrying dead mass costs you exponentially. Every one of those enormous machines, every gantry and flame trench and countdown, buys you a delta V measured in single-digit kilometers per second. To put that against the numbers coming in a moment, the third stage of a Saturn V, the one that pushed Apollo out of Earth orbit and toward the moon, delivered roughly 3.2 kilometers per second. That was the most powerful upper stage ever built by anyone, at the peak of the largest engineering program in history, and it moved the needle by 3. Hold that figure. It is about to become uncomfortable. There is one last consequence of inherited motion that catches people out, and it is worth sitting with because it inverts an intuition almost everyone holds. If a spacecraft in interplanetary space shuts off its engines and does nothing at all, it does not drift to a halt, and it does not fall into the sun. It keeps orbiting exactly as it was, indefinitely. Stopping is not the default state of anything in space. Stopping is a maneuver, and it is one of the most expensive maneuvers there is. This is why falling into the sun is genuinely harder than leaving the solar system altogether, a fact we will come back to because a spacecraft is doing it right now. So the inherited speed is the whole problem. It is free when you go with it, and ruinous when you go across it. The obvious question is, how ruinous? Not in adjectives, in numbers, and the 2 numbers that answer it are the reason nothing has ever gone up. Everything in this story comes down to 2 numbers, and once you have heard them, the rest of the video is only a matter of watching them play out. Here is the first one. To escape the Sun's gravity completely, starting from the distance the Earth orbits at, an object needs to be travelling at about 42.1 kilometers per second relative to the Sun. Reach that speed in the right direction, and you're on a path that never comes back. You climb out of the solar system's gravity well and keep going, slowing down forever, but never quite stopping. Now subtract what you already have. You start with 29.8, handed to you free by the planet you launched from. So the engines only have to supply the difference, about 12.3 kilometers per second. That is a large number. It is roughly 4 times what the mightiest upper stage ever built delivered to Apollo. But it is not an impossible number, and we know it is not, because it has been achieved 5 separate times using powerful upper stages combined with gravity assists from planets along the way. 12.3 kilometers per second buys you a ticket out of the solar system in the direction you were already going. Here is the second number. To change the plane of your orbit, to turn out of the flat sheet everything is riding in, orbital mechanics gives you a specific relationship. The velocity change required equals twice your current orbital speed, multiplied by the sine of half the angle you want to turn through. It is a simple formula, and it is completely unforgiving, because the thing it scales with is not the size of your spacecraft, or the distance you want to travel. It is how fast you're already moving. Put 90 degrees into that formula at Earth's orbital speed, and the answer comes out at about 42.1 kilometers per second. Sit with that for a moment, because it is the same number as solar escape velocity, and that is not a coincidence. Turning 90 degrees at speed v cost v times the square root of 2, and escaping from a circular orbit also requires the square root of 2 times your orbital speed. 2 completely different maneuvers, arriving at the same figure by different routes. But the comparison that matters is not between 42 and 42, it is between what your engines have to supply. Escaping the solar system outward, 12.3 kilometers per second, turning 90 degrees to face genuinely up, 42.1. Going up is roughly 3.5 times more expensive than leaving, and because of the rocket equation, 3.5 times more expensive does not mean 3.5 times more fuel, it means something closer to 1,000 times more fuel. A chemical stage delivering 12.3 kilometers per second needs a mass ratio of roughly 16 to 1, 16 tons on the pad for every ton that arrives. A chemical stage delivering 42.1 needs a mass ratio in the region of 10,000 to 1. That is not a hard engineering problem. That is not a problem that gets solved with a bigger budget or a better alloy. It is a number that says no. It is worth being concrete about what a direct attempt would actually look like, because the abstraction hides how absurd it is. Suppose you wanted to send a modest scientific payload, a few hundred kilograms, about the mass of a grand piano, onto a genuinely perpendicular orbit around the Sun, using chemical propulsion and nothing else. Working backwards through the rocket equation, the launch stack required would be measured in thousands of tons, and that is before you have accounted for the structure needed to hold thousands of tons together, which itself has to be lifted. Nobody has ever seriously proposed building it, not because of a lack of ambition, but because the proposal writes itself into a corner in the first paragraph. New Horizons left Earth at about 16.3 kilometers per second, the fastest departure speed ever achieved from a launch pad, and even that spacecraft needed a slingshot past Jupiter in February of 2007 to arrive at Pluto within a working lifetime. Most people find this backwards, and it is worth understanding why the intuition fails. On Earth, turning is cheap. You steer a car around a corner and it costs you almost nothing. A little friction in the tyres, a slight loss of speed. Accelerating from 30 to 60 cost you fuel. Turning left cost you nothing you would notice. So the instinct says that changing direction should be the easy manoeuvre, and changing speed should be the hard one. In orbit, it is precisely the other way around, because in orbit there is nothing to push against. A car turns by pressing sideways on a road, and the road pushes back for free. A spacecraft has no road. The only thing it can push against is its own exhaust. So a turn is not a turn, it is a subtraction and an addition. You must cancel the velocity you have in the old direction, and build up an equal velocity in the new one, and both halves come out of the same tank. Draw it as a triangle, your old velocity vector, your new velocity vector, and the third side connecting their tips is the velocity change your engines have to produce. When the angle between them is small, the third side is short. When the angle is 90 degrees, the third side is longer than either of the others, which means direction, in space is expensive in exact proportion to speed. The faster you're going, the more it costs to face somewhere else, and you are going very fast. There is one way to soften the blow, and mission designers use it constantly. If you are going to perform a burn anyway, a departure burn, an orbital insertion, a course correction, you can fold a small inclination change into it, angling the thrust slightly out of plane rather than making two separate maneuvers. Because velocities add as vectors rather than as numbers, doing both at once is always cheaper than doing them one after the other. This is why almost every spacecraft that has ever left the ecliptic even slightly did so, by tilting a burn it was already committed to, or by adjusting the geometry of a flyby it was already going to make. Nobody has ever launched a mission whose purpose was the turn. The partial numbers are just as sobering as the full one. A 10-degree plane change at Earth's orbital speed costs about 5.2 kilometers per second, comparable to the entire propulsion budget of a mission to Mars spent on tilting slightly. 30 degrees cost about half your orbital speed. 60 degrees cost a full orbital speed, as much velocity change as the Earth's entire annual motion, spent on nothing but pointing. Take a moment with what that means, because it is larger than a fact about rockets. Every mission human beings have ever flown went where the inherited motion allowed it to go. Every trajectory was a negotiation with a velocity nobody chose. We have never selected a direction in space and then travelled in it. We have only ever selected how fast to go in the direction we were already travelling, and which planets to let redirect us along the way. Planets that are themselves obeying the same inherited motion. Direction out here is not something you steer toward. It is something you are handed, and then you spend your entire mission making the best of it. There is one loophole in the arithmetic, and it is the only reason any of this ever went anywhere. Look again at what the plane change formula depends on. It scales with your current orbital speed, not your mass, not your destination, not the strength of the sun's gravity where you happen to be, just how fast you're moving right now. An orbital speed is not fixed. Objects further from the sun move more slowly, because they need less speed to hold themselves against a weaker pull. The Earth, at 150 million kilometers out, does 29.8 kilometers per second. Jupiter, more than 5 times further, does about 13. So if you can get yourself out to Jupiter's distance before you attempt the turn, that same 90-degree change costs about 18.5 kilometers per second instead of 42, before anybody helps you at all. Distance from the sun buys a discount on direction, and the discount is enormous. Push the logic further, and it stops being a discount and starts being a joke. Out at 1,000 times the Earth's distance from the sun, orbital speed has fallen to a few hundred meters per second, and a 90-degree turn out there would cost less than a modest satellite maneuver in low Earth orbit. In principle, you could climb out to the far reaches of the sun's territory, turn almost for free, and then fall back inward on a completely different plane. Orbital mechanics has a name for the general strategy, the bi-elliptic transfer, and for large angle changes it genuinely is cheaper than a direct turn. The catch is time. The trip out and back would take centuries, and nobody has ever designed a mission around a maneuver that outlives every person who authorized it. Which is the quiet theme running under all of this. The plane can be beaten, but only by something with more patience than a human institution has ever had. There is a catch, and it is a genuine tension in mission design. Rocket burns are most efficient deep in a gravity well while moving fast, an effect named after the Romanian engineer Herman Oberth. Plane changes are cheapest, far out while moving slowly. The two rules point in exactly opposite directions, and no trajectory can satisfy both. Every mission that has ever gone anywhere interesting is a compromise between them. It should be said plainly that none of this is a barrier in the sense of being forbidden. Nothing in the laws of physics prohibits a spacecraft from travelling perpendicular to the ecliptic. There is no conservation law standing in the way, no rule that says the direction is closed. Every equation involved will happily describe the maneuver. They simply also describe the bill, and the bill is the answer. This is not a locked door. It is a price tag, written in a currency we cannot print, on a direction that is otherwise completely open, which brings us to a spacecraft weighing about as much as a small motorcycle, carrying no camera at all, sitting in the payload bay of the Space Shuttle Discovery on a launch pad in Florida in the autumn of 1990, waiting to attempt the only genuine assault on this problem that anyone has ever mounted. In the 1970s, before anyone had built the thing, the plan was to do it twice at once. The mission was called the International Solar Polar Mission, and it was beautifully symmetrical on paper. 2 spacecraft, one built by the Americans and one by the Europeans, launched together, thrown out to Jupiter together, and then flung by Jupiter's gravity in opposite directions, one climbing over the Sun's north pole while the other dropped under its south, both taking measurements simultaneously, so that for the first time in history, somebody could see the whole star at once, rather than watching one hemisphere and guessing about the other. In 1981, NASA cancelled its half budget. The European Space Agency was left holding a mission designed for 2 spacecraft, with only 1 spacecraft to fly it, and rather than abandon the idea, they rebuilt it as a solo effort, with NASA providing the launch, the tracking network, and the power supply. Then, in January of 1986, the Space Shuttle Challenger broke apart 73 seconds after liftoff. The shuttle fleet was grounded, and the launch slipped from May of 1986 to October of 1990. By the time it finally flew, the spacecraft had been renamed. It was called Ulysses, and the name was not taken from Homer. It came from Dante and from Tennyson, the version of the character who, having survived everything and come home, cannot stay, and sails west past the edge of the known world with an old crew and does not come back. Somebody at the agency chose that deliberately. It is difficult to read the mission profile and think they chose wrong. On the 6th of October, 1990, the Space Shuttle Discovery lifted off from Kennedy Space Center on mission STS-41. In the payload bay sat an object about the size of a garden shed and the mass of a small motorcycle, 370 kilograms, including 33.5 kilograms of hydrazine for course corrections. It carried 9 instrument packages, magnetometers, particle detectors, a radio and plasma wave experiment, a cosmic ray telescope, a dust counter, an instrument for detecting solar X-rays and cosmic gamma-ray bursts. It carried no camera, not one. Every kilogram had been argued over, and imaging lost. Remember that, because it cost us something specific 33 years later. Its power came from a radioisotope thermoelectric generator, a block of plutonium dioxide whose natural decay produces heat, converted directly into electricity with no moving parts. Solar panels were never an option, because the route to the Sun's poles runs outward first, and at Jupiter's distance sunlight is only about a 27th as strong as it is at Earth. To look at the Sun from above, you have to go somewhere the Sun is barely any use to you. Once clear of the shuttle, a 2-stage solid-fuel booster stack fired, an inertial upper stage, then a payload assist module. When the last of it burned out, Ulysses was travelling away from Earth faster than any object had ever been thrown from this planet, a departure energy higher than anything before it, and still among the highest ever achieved. And it was not aimed at the Sun. It was aimed at Jupiter, in the completely wrong direction, 5 times further out than it needed to be, on a journey that would take 16 months. It is the 8th of February, 1992. Ulysses has been falling outward for 490 days. Jupiter fills the sky ahead of it, a planet 11 times the width of the Earth, more massive than everything else orbiting the Sun combined, its cloud bands turning over one another in a system of storms older than recorded history. The spacecraft is going to pass within about 6 Jupiter radii of the centre of it, threading through the outer edge of the most intense radiation environment in the solar system, and there is nothing anyone on Earth can do to help it. A radio signal takes roughly 40 minutes to cross the distance each way. Whatever happens has already happened by the time anyone knows. Inside that radiation environment, the particle counters are saturating. Jupiter's magnetosphere accelerates electrons to energies that punch straight through spacecraft shielding, and this small European machine has to cross the outer edge of it, carrying instruments built to detect exactly the sort of particles that are about to overwhelm them. There is no shelter and no alternative route. The geometry that makes the maneuver possible requires passing exactly here, and nothing fires. That is the part worth holding on to. No engine burns, no thruster lights. The hydrazine stays in its tank. Ulysses simply falls past Jupiter, and Jupiter's gravity takes hold of it, and the trajectory bends, not sideways, the way almost every other gravity assist in history has bent a spacecraft, but upward, out of the flat sheet that every planet and moon and asteroid and comet in this system has been riding since before the Earth existed. The maneuver takes hours. It costs nothing. Jupiter gives up a quantity of orbital momentum so small that no instrument built by human beings could detect it, a planet the mass of 300 Earths, slowed by an amount that would not register in a million years of measurement, and in exchange, a 370-kilogram machine is thrown out of the plane of the solar system, the most expensive maneuver in the history of spaceflight, and nothing was spent. The orbit Ulysses ended up on was inclined about 80 degrees to the ecliptic, near enough to perpendicular that the difference is a detail, with a period of about 6.2 years, an aphelion out near Jupiter, and a perihelion inside the Earth's orbit. Every 6 years it would fall in from the outer solar system, sweep rapidly over one solar pole, cross the ecliptic near the Sun, sweep over the other pole, and climb back out again. It is worth explaining why anyone wanted this badly enough to spend 2 decades getting there. The Sun's poles are not a scenic detail, they are where the star's magnetic field is anchored. That polar field flips over completely at every solar maximum, north becoming south and south becoming north, roughly every 11 years, and its strength at solar minimum turns out to be the single best predictor of how violent the following cycle will be. Space weather, the flares and coronal mass ejections that knock out satellites, disturb power grids and force airliners off polar routes, is driven by that field. We had been trying to forecast it for decades while looking at the star Edge-On from inside its equatorial plane, which is roughly like trying to understand a hurricane by standing at the edge of it and never once seeing the eye. The first South Polar Pass ran from June to November of 1994. The first North Polar Pass ran from June to September of 1995. For the first time, a human instrument was looking down at our star. What it found was worth the wait. Every spacecraft before it had sampled the solar wind from within the ecliptic, because every spacecraft before it had been stuck in the ecliptic, and the wind we had measured for decades, slow, gusty, variable, around 400 kilometers per second, turned out to be the unrepresentative case. Over the poles, Ulysses found a completely different wind, fast, smooth, remarkably steady, pouring out of the polar coronal holes at around 750 kilometers per second. During solar minimum, that fast wind dominates almost the entire high-latitude sky. We had spent 30 years studying the exception and calling it the rule. It also found something nobody predicted. The strength of the Sun's magnetic field turned out to be roughly the same regardless of latitude. The poles are not magnetically distinct from the equator in the way everyone had assumed, and it measured how galactic cosmic rays, arriving from interstellar space, find their way into the solar system over the poles rather than through the ecliptic. The Jupiter encounter itself produced a bonus nobody had planned for. Because Ulysses passed through the Jovian system on a steeply inclined path rather than the usual equatorial one, it sampled regions of Jupiter's magnetosphere at high latitudes that no spacecraft had ever visited, territory that Galileo, arriving 3 years later on a conventional orbit, would never reach, and that Juno would not properly explore for another 2 decades. A mission designed to leave Jupiter behind ended up returning data about Jupiter that nothing else could get, purely because of the angle it was travelling at. It even got lucky in ways nobody designed for. In May of 1996, Ulysses passed through the ion tail of comet Hyakutake, not near the comet, but roughly 3.5 times the Earth-Sun distance downstream of it, which established that Hyakutake had the longest comet tail ever recorded, more than 500 million kilometers of it. The spacecraft did it again with Comet McNaught in 2007. It was not looking for comet tails. It was simply the only object that had ever been in those places. Ulysses completed a second polar orbit in 2000 and 2001, this time at solar maximum, and a third in 2007 and 2008. On that third pass, it measured a solar wind weaker than at any point in the 50 years since measurements began, a genuinely unexpected result about our own star, visible only from above it. The mission was designed to last 5 years. It lasted 18.5. It ended on the 30th of June 2009, and the reason it ended is quietly perfect. The plutonium supply had decayed to the point where there was no longer enough waste heat to keep the hydrazine lines above their freezing point of about 2 degrees Celsius. Not a broken instrument, not a failed antenna. The spacecraft simply got too cold to steer, so it can be done. One spacecraft in 65 years has climbed out of the plane of the solar system and looked down at our star. It reached 80 degrees, not 90, and it had no camera, so it could measure the poles but never photograph them. The question is how a 370-kilogram machine achieved a maneuver that would have required a launch stack of thousands of tons? And the answer is that it did not achieve it. It found a way not to pay for it, and the way it did that tells you more about this problem than the mission itself. Let us step back for a moment and put the pieces together, because we are about halfway through, and the shape of the thing is worth seeing whole. The solar system is a flat disk, ironed into that shape 4.5 billion years ago by collisions that cancelled every particle's vertical motion and threw the difference away as heat. Everything born inside that disk inherited its direction of travel, including the Earth, including you, including every object ever launched from the Earth's surface, at 29.8 kilometers per second. Going anywhere within the disk means spending that inherited motion, which is cheap. Going out of the disk means cancelling it, which is not, about 42 kilometers per second to turn 90 degrees, against about 12 to leave the solar system entirely in the direction you were already pointing, and one spacecraft once got to 80 degrees anyway. So how? Two separate effects were stacked on top of each other, and neither one alone would have been enough. The first is the discount that comes with distance. The cost of a plane change scales directly with how fast you're currently moving, and how fast you're moving depends on how far you are from the Sun. Close in, gravity is strong and orbits are quick. Further out, gravity is weaker, orbits are slower, and the same turn costs less. At Earth's distance, 90 degrees costs about 42 kilometers per second. Out at Jupiter's distance, 5.2 times further from the Sun, orbital speed has dropped to about 13 kilometers per second, and the same 90-degree turn costs about 18.5. That is not a small saving. It is more than half the price, gone, purely for standing somewhere else. Ulysses spent 16 months flying in exactly the wrong direction for one reason: to arrive at a place where the maneuver it wanted was affordable. Except 18.5 kilometers per second is still far beyond anything a spacecraft that size could carry. So the second effect had to do the rest. A gravity assist looks, at first glance, like something for nothing. A spacecraft approaches a planet, curves around it, and leaves faster than it arrived, or pointing somewhere completely different, without burning a drop of fuel. People sometimes describe it as free energy, which understandably makes anyone who knows the conservation laws uneasy. Nothing is free. The energy is borrowed, and it is borrowed from the planet. Here is what actually happens. As the spacecraft falls toward the planet's gravity accelerates it. As it climbs back away on the other side, that same gravity decelerates it by precisely the same amount. Measured relative to the planet itself, the spacecraft leaves at exactly the speed it arrived at. Nothing has changed at all, but the planet is not sitting still. The planet is orbiting the Sun, and if the spacecraft approaches from the right side, trailing behind the planet's own motion, then during the encounter it is effectively being dragged along by a moving object. Relative to the planet, nothing has changed. Relative to the Sun, the spacecraft has picked up a share of the planet's orbital velocity. If that is hard to picture, use a tennis ball and a train. Throw a tennis ball at a wall and it bounces back at the speed you threw it. Throw the same ball at the flat front of a train coming toward you at 100 kilometers per hour, and it comes back very much faster, not because you threw it harder, but because the wall was moving. Relative to the front of the train, the ball approached and departed at the same speed. Relative to the ground, it gained twice the train's velocity. The train lost a corresponding immeasurably small amount of its own. That is a gravity assist, with gravity doing the work of the collision so that nothing actually has to touch. And the planet pays for it. It loses exactly as much momentum as the spacecraft gains. A real, physical transfer governed by the same conservation laws that describe every collision in the universe. Jupiter has a mass of about 318 Earths. Ulysses had a mass of 370 kilograms. The momentum Jupiter surrendered on the 8th of February 1992 is a number so small that no instrument humanity will ever build could measure it, and Jupiter's orbit will have recovered from it long before it matters. But it happened. Somewhere in the bookkeeping of the solar system, Jupiter is very slightly further from the Sun than it would otherwise have been, because of us. Most gravity assists are used to change speed and to bend a trajectory sideways, within the plane, aiming a spacecraft at its next destination. Ulysses did something different. It approached at precisely the angle needed to have its path bent not sideways but upward, trading a share of Jupiter's own colossal orbital momentum for the one thing no engine could deliver. Jupiter did the work. Jupiter is the only object in the solar system that could have. That is the point at which this stops being a story about a clever mission and becomes a story about a constraint. You are not on the disk, you are in it, and you cannot walk out of something you are inside of. Not at these speeds, not with these engines. You can only be thrown, and there is exactly one thing in the solar system with an arm strong enough to throw you, and it lives 800 million kilometers away and takes 12 years to come back around. There is also a subtlety in where along an orbit you attempt to turn, and Ulysses obeyed it precisely. Any elliptical orbit has a fast end and a slow end. A spacecraft moves quickest at its closest approach and slowest at its furthest. Because the price of a plane change tracks your speed at the moment you make it, the cheapest possible instant to change plane is at the far end of the ellipse, at the slowest point of the whole orbit. Mission designers fold this into everything. It is the same rule that says go out before you turn, applied at the scale of a single loop rather than a whole solar system, and it is the reason the geometry of Ulysses' encounter had to be right to within a very small margin. There was no second attempt available. Get the approach angle wrong at Jupiter, and the mission is simply a probe on a strange orbit going nowhere in particular, with no fuel to fix it and no planet within reach to ask again. Nobody has repeated the maneuver. It is worth being clear about why, because it is not a failure of imagination or of interest. Scientists have wanted better observations of the sun's poles continuously since Ulysses returned its first data. The problem is that every route to them runs through the same bottleneck. Jupiter has to be in the right place. Its orbital period is about 11.9 years, and the geometry that allows a Jupiter encounter to produce a steep out-of-plane trajectory rather than an ordinary in-plane one comes around on its own schedule, not ours. A mission has to be funded, built and launched to match a window set by a planet. Then there is the cost of the detour itself. Ulysses spent 16 months travelling away from its target before the real manoeuvre could even begin, and its final orbit had a 6-year period, which meant its polar passes came in short bursts separated by years of travelling through empty space at high inclination doing very little. And there is a third cost, which is the most interesting one and the least obvious. The moment you leave the plane, you lose access to everything else in it. Consider what a mission gives up. Staying in or near the ecliptic means every planet is available as a potential assist, and gravity assists are not a luxury. They are the entire reason the outer solar system is reachable at all. Voyager 2 visited Jupiter, Saturn, Uranus and Neptune on a fraction of the fuel that 4 separate missions would have required, and it could do that only because the 4 planets share a plane, and because a rare alignment that recurs about once every 176 years put them in a line. That kind of route does not exist above the ecliptic. There are no planets up there to help. There is no asteroid belt to sample along the way, no Trojan swarm, no short-period comets, no moons, no rings, no anything. The plane is where the gravity is. The plane is where the mass is, where the free momentum is, where the efficient routes are, where nearly every object worth studying happens to be. Leaving it means surrendering the entire toolkit that makes space travel affordable in exchange for empty space and a viewing angle. It is worth saying what you would actually get if you paid. A spacecraft high above the North Ecliptic Pole would have the one view nothing has ever had. The solar system seen from directly overhead, the way you might look down at a spinning record from above rather than squinting along its edge. Every planet, every asteroid, the whole disk laid out flat beneath you in a single frame, the geometry of the thing visible in one glance instead of reconstructed from centuries of measurements taken from inside it. Ulysses came closer to that than anything else ever has and could not photograph it. Nobody has ever seen the shape of the place we live from outside. There have been proposals, there have been many. Mission concepts for a solar polar observer have been submitted, studied, costed and shelved repeatedly since the 1990s, and they all founder in the same place, not on the science case, which is strong and has only got stronger, but on the propulsion line of the budget. Every serious study reaches the same conclusion Ulysses reached in 1990. You either borrow Jupiter, or you spend a decade creeping up on it, or you do not go. That is not a locked door. It is much worse than a locked door, because a locked door can be broken. It is a current, one that every other path in the solar system happens to be flowing with, and that you would have to swim against alone, with no help from anything, for no reward except the view. Which leaves one option for anybody who still wants to go up. If you cannot pay the price in one installment, and you cannot wait for Jupiter, then you have to find a way to pay it a few degrees at a time. and 2 spacecraft flying right now are doing exactly that. On the 16th and 17th of March 2025, a spacecraft took a photograph that no human being had ever seen the like of. It was a picture of the bottom of the Sun. The spacecraft is called Solar Orbiter. It is led by the European Space Agency with NASA participation, and it launched on the 10th of February 2020. It did not go to Jupiter. It could not afford to, and it did not need to because it was built around a completely different answer to the same problem. Instead of one enormous borrowed push, take many small ones and be prepared to wait years for them. Its route runs past Venus, over and over. Each flyby of Venus tilts its orbit by a few degrees. A small nudge, nothing dramatic, the sort of adjustment that would be worthless on its own. But it comes back, and it does it again. And each time the inclination creeps a little higher, bought at almost no fuel cost, paid for instead in years. By February of 2025, after another Venus encounter, Solar Orbiter had accumulated enough of those nudges to reach about 17 degrees below the Sun's equator, and it began what the mission calls its high latitude phase. 17 degrees does not sound like much. Ulysses reached 80. But 17 degrees is enough to see over the curve, and Solar Orbiter had the one thing Ulysses did not. It had cameras. 3 instruments recorded the South Pole over those March days: the polarimetric and helioseismic imager, which maps the Sun's magnetic field, the extreme ultraviolet imager, which sees the million-degree outer atmosphere, and SPICE, which reads the composition and motion of different layers by their spectral signatures. The full pole-to-pole dataset from that first high-latitude pass came back to Earth by October of 2025. The extended mission is expected to climb to somewhere around 33 degrees. What the images showed was itself a small surprise. The Sun's south pole, viewed for the first time, was magnetically untidy. Patches of north polarity and patches of south polarity sitting together in the same region, rather than the clean single polarity you would expect from a bar magnet. That mess is not an error. It is what a magnetic pole looks like during the handful of years around solar maximum, when the star's global field is in the middle of turning itself completely upside down. We had known the field flips, because we could see the consequences from down here in the plane. Nobody had ever watched it happen at the pole where it happens. Think about the arithmetic of that achievement across the 2 missions. Ulysses got to 80 degrees in 16 months by borrowing the largest planet in the solar system and could only measure. Solar Orbiter got to 17 degrees in 5 years by asking Venus repeatedly for small favours and could photograph. Between them, 35 years apart, they represent the total human experience of looking at our own star from above or below its equator. There is a second spacecraft flying right now that is solving the mirror image of this problem, and the symmetry between them is worth sitting with. Parker Solar Probe launched on the 12th of August 2018, and its goal was to get close to the Sun, closer than anything ever had, close enough to fly through the outer atmosphere and sample it directly. That sounds like it should be easy. The Sun is enormous, and its gravity is relentless. Surely falling toward it is the natural thing for anything to do. It is not, and the reason is the same number that has haunted this entire subject. A spacecraft launched from Earth starts with 29.8 kilometers per second of sideways motion. That sideways motion is precisely what keeps the Earth from falling into the Sun, and any object that inherits it inherits the same immunity. To fall inward, you have to get rid of it, and getting rid of it is exactly as expensive as adding it. Falling into the Sun is genuinely harder than leaving the solar system. So Parker did what Solar Orbiter does, in reverse. 7 flybys of Venus, spread over about 7 years, each one shaving away a little more of that troublesome tangential speed, each one letting the orbit shrink and tighten. On the 24th of December 2024, it passed within about 6.1 million kilometers of the solar surface, 3.8 million miles, well inside the orbit of Mercury, traveling at roughly 192 kilometers per second. That is about 430,000 miles per hour, and it makes Parker Solar Probe the fastest object human beings have ever built. The reason for going was a pair of questions physics has been unable to answer from a distance. The Sun's visible surface is around 5,500 degrees Celsius, and the thin outer atmosphere above it, the corona, the pale halo you see during a total eclipse, is over 1 million. Heat is not supposed to flow from a cooler place to a hotter one. Something is depositing energy up there, and after a century of theories, nobody has settled which mechanism dominates. The only way to find out was to fly into it and take measurements, which is what Parker did, becoming the first object to enter the atmosphere of a star. Its heat shield is a carbon composite foam sandwich about 11 centimeters thick. The face of it reaches around 1,370 degrees Celsius. Behind it, the instruments sit at roughly room temperature. Ulysses needed to climb out of the plane. Parker needed to fall out of an orbit. Neither could be done with engines. Both were done by asking planets for repeated small favours over years. The most extreme destinations in the solar system, straight up and straight in, are reached the same way by patience and borrowed momentum and never by power. There is one technology that might eventually change this, and it works by inverting the usual assumptions about what a rocket is for. Electric propulsion, ion drives, produce almost no thrust at all. NASA's N-Star engine, the first flown on a science mission, generated about 92 millinewtons. That is roughly the weight of a sheet of paper resting on your palm. You could hold one at full power and barely notice. What ion engines have instead is efficiency. They throw their exhaust out 10 times faster than a chemical rocket can, which means they get 10 times as much velocity change out of every kilogram of propellant, and they can keep going for years. The way that plays out in practice is almost comic. An ion-powered spacecraft accelerating at full thrust takes something like 4 days to go from standing still to the speed of a car on a motorway. It is the slowest acceleration ever deliberately engineered, but it does not stop after 8 minutes the way a chemical stage does. It keeps pushing for months, and then for years, and the total velocity change accumulates into numbers no chemical engine of the same mass could approach. NASA's Dawn spacecraft is the proof. It launched on the 27th of September 2007, flew to the asteroid Vesta, entered orbit, spent 14 months there, then left orbit and flew to the dwarf planet Ceres and entered orbit there. The first spacecraft ever to orbit 2 separate bodies beyond the Earth, which is only possible if you can afford to stop twice. Over its mission, it accumulated a total velocity change of about 11.1 kilometers per second from its own engines. That is still the record for any spacecraft's own propulsion, and no chemical system of a comparable size could have come within a factor of several of it. Then there are sails. A solar sail carries no propellant at all. It is pushed by the momentum of sunlight itself, which is minute but entirely free and never runs out. Japan's Ikaros demonstrated it in 2010 with a sail 20 meters across and 7.5 micrometers thick, thinner than a human hair by a factor of 10, steering itself by switching the reflectivity of liquid crystal panels embedded in its edges. The Planetary Society flew LightSail 2 in 2019. NASA launched its Advanced Composite Solar Sail system in April of 2024. And sails have one property that matters enormously here. They get stronger the closer to the sun you take them, because sunlight is more intense there. A long-standing mission concept called the Solar Polar Imager proposes exactly this. Spiral a sail inward to about half the Earth's distance from the sun, where the photon pressure is 4 times higher, and then use that pressure to crank the orbital inclination up over a period of years until the spacecraft is at something like 75 degrees. No Jupiter, no borrowed planet, just sunlight, pushed against patiently for a decade. It is worth noticing what all 3 of these technologies have in common, because it is the same thing Ulysses discovered by accident. None of them tries to win the argument in a single burn. Ion drives, solar sails, and repeated planetary flybys are all ways of converting time into velocity change, of substituting patience for power, because power at the required scale simply does not exist and shows no sign of arriving. A chemical rocket spends its entire capability in a few minutes and then coasts forever. Everything that has ever made real progress against the plane has done the opposite, pushed almost imperceptibly, for years, and let the arithmetic accumulate. Nothing like it has been funded. But it is the only credible plan anyone has ever written down for choosing a direction in space and simply going there. So the plane can be climbed, slowly, at enormous cost in time. And yet none of that is the same thing as leaving. Solar Orbiter is not going anywhere. It is circling the sun on a tilted track. Ulysses circled for 18 years and then went cold. Parker is falling inward. There are 5 objects that really are leaving. Every article ever written about them says so, and they are the reason this question has an answer nobody expects. 5 objects built by human hands are on trajectories that will carry them out of the Sun's planetary region and eventually into the space between the stars. They are the only 5, and there is no 6th planned. Pioneer 10 launched on the 2nd of March 1972. It was the first spacecraft to cross the asteroid belt, the first to fly past Jupiter, and for a while the most distant human object in existence. Its last faint signal was received on the 23rd of January 2003, from a distance of about 80 times the Earth-Sun separation. It is heading in the general direction of the star Aldebaran in Taurus, which it would reach in something like 2 million years if anything was still working. It is easy to forget how uncertain that first crossing was. Before Pioneer 10, nobody knew whether the asteroid belt could be flown through at all. The belt was widely imagined as a hazard field of tumbling rock, and there were serious people who thought a spacecraft attempting to cross it would be destroyed. Pioneer 10 went through and reported almost nothing. A few dust impacts, no drama, an enormous volume of space with a very small amount of material spread thinly across it. Everything that has gone to the outer solar system since has gone because that one machine went first and found the way empty. Pioneer 11 launched 13 months later, on the 5th of April, 1973. It made the first flyby of Saturn. Contact was lost in November of 1995 when its power supply could no longer run a transmitter. It is heading toward the constellation Aquila. Both Pioneers carry an engraved aluminium plaque designed by Carl Sagan, Frank Drake, and Linda Salzman. Sagan. 2 human figures, a diagram of the hydrogen atom, and a map showing the position of the Sun relative to 14 pulsars. Nobody involved believed it would ever be found. They did it anyway. Voyager 2 launched on the 20th of August 1977 and remains the only spacecraft ever to visit Uranus or Neptune. It crossed the heliopause on the 5th of November 2018 at about 119 times the Earth-Sun distance. It is currently around 143 of those units out, receding at about 3.1 per year. Voyager 1 launched 16 days later, on the 5th of September 1977, on a faster trajectory that let it overtake its twin. It crossed the heliopause on the 25th of August 2012 at about 121 units. It is now around 170 units from Earth, receding at about 3.5 units per year, and it is the most distant object our species has ever made. The difference between the 2 Voyager heliopause crossings is worth a sentence, because it was pure luck. Voyager 1's plasma instrument had failed years before it got there, so the most direct measurement of the boundary had to be inferred indirectly from plasma wave data. Voyager 2's plasma instrument still worked. When it crossed 6 years later, it returned the clean, direct density measurements that Voyager 1 could not, and the 2 datasets together showed that the boundary is not a smooth, uniform surface at all. The conditions on the far side differed noticeably between the 2 crossing points, which are separated by a considerable stretch of sky. New Horizons launched on the 19th of January 2006 at 16.3 kilometers per second, the fastest departure from Earth ever achieved. It used a Jupiter assist in February of 2007, flew past Pluto on the 14th of July 2015, and past a small Kuiper belt object called Arakoth on New Year's Day 2019. It is still going, still close to the ecliptic. There is a small irony buried in New Horizons' record. It left Earth faster than anything before or since, and it is now the slowest of the 5 outbound spacecraft, moving at about 14 kilometers per second against Voyager 1's 17. The reason is that it spent the intervening years climbing. Every kilometer a spacecraft travels away from the Sun is a kilometer uphill, and the Sun's gravity takes its toll continuously and without exception. The Voyagers were given more energy by their planetary encounters than New Horizons was, and so they arrived at the top of the hill still moving faster. Speed at launch is not the same as speed later, out here. Now the detail that changes everything. Voyager 1 is not travelling in the plane of the solar system. It is climbing out of it at about 35 degrees to the north, aimed roughly at the solar apex, the direction the Sun itself is moving through the local neighbourhood of stars. Voyager 2 is not in the plane either. It is descending at about 48 degrees to the south, toward the constellations Sagittarius and Pavo. 48 degrees. That is more than half of the 90 degrees we have spent this entire video establishing as unaffordable. If you have been building a counterexample in your head for the last hour, this is it, and it looks like a good one. It is not. It is the opposite of one, and the reason is the most important thing in this part of the story. Neither of those inclinations was bought. Not 1 gram of propellant was ever spent to produce them. Both were side effects, accidents of geometry, handed over free by planets, as the price or the consequence of doing something else entirely. It is the 12th of November, 1980, and Voyager 1 is falling towards Saturn. The decision that governs the next several billion years of this spacecraft's existence was made years earlier, in a room in Pasadena, by people looking at trajectory plots. It was a straight choice, and it could not be avoided or deferred. Option 1, pass close beneath Titan, Saturn's largest moon, a world with a thick orange atmosphere that nobody had ever seen through, and swing behind the ring system for a look at its structure from the far side. Option 2, skip Titan, take a different approach geometry, and continue on to Uranus and Neptune, 2 planets no spacecraft had ever visited or would visit for another decade. The spacecraft cannot do both. The Titan encounter requires an approach that will bend its path up and out of the plane of the solar system permanently, and once bent it will never come back down. There are no more planets above the ecliptic. Choosing Titan ends the tour. They chose Titan. Voyager 1 passed about 4,000 kilometers above its cloud tops, found an atmosphere denser than Earth's, could see nothing through it at all, and was thrown north. That is the whole mechanism. A meeting, a trajectory plot, a moon. And 46 years later a machine is climbing away from the plane of the solar system at 3.5 times the Earth-Sun distance every year, on a heading that was decided as a side effect of wanting to look at a moon it could not even see the surface of. Voyager 2's 48 degrees south has an equally mundane origin. On the 25th of August 1989, it passed about 4,950 kilometers above Neptune's North Pole, the closest approach of the entire Grand Tour. That geometry was chosen for one reason. It was the only path that would then carry the spacecraft down past Triton, Neptune's large, backwards orbiting moon. Passing that close over the North Pole of a planet with that much mass bends a trajectory downward, hard. Voyager 2 got Triton, and it got a permanent 48 degrees southward heading in the same transaction, and nobody had to pay for either. Look at when and where both of those turns happened. Far from the Sun, where orbital speeds are low and plane changes are cheap, and performed by planets which have momentum to spare and never send an invoice. It is exactly the Ulysses trick, executed by accident, twice by spacecraft that were trying to do something else. That entire Grand Tour was itself an accident of timing, the alignment of Jupiter, Saturn, Uranus, and Neptune that let a single spacecraft chain 4 gravity assists together recurs roughly once every 176 years. It happened to fall in the late 1970s. Had anyone been ready in 1801, or were anyone to wait until 2153, the same route would be available. In between, it simply is not there. Both Voyagers carry the golden record, a gold-plated copper phonograph disc holding 115 images, greetings in 55 languages, natural sounds and 90 minutes of music, with a stylus and instructions engraved on the cover. It is the strangest cargo ever loaded onto a vehicle, a message with no address, no delivery date, and no realistic prospect of arrival, carried by machines whose trajectories were determined by fuel budgets and the position of moons. It is worth pausing on what those machines are now. Voyager 1 transmits with about 23 watts of power, roughly a dim household light bulb, from a distance where the signal arriving at the enormous dishes of the Deep Space Network has a strength of well under a billionth of a watt. Its plutonium supply weakens by around 4 watts every year, and instruments have been switched off one at a time to keep the essential ones running. First the cameras, then the heaters, then whatever could be spared. A handful still report on cosmic rays, magnetic fields, and plasma waves. Current estimates give both spacecraft until somewhere in the late 2020s or early 2030s before the last instrument goes quiet and they become permanently silent objects on fixed paths, which leaves one loose thread hanging, and it is the one this entire video has been walking toward. Both Voyagers are routinely described as having left the solar system. They crossed the heliopause, Voyager 1 in 2012, Voyager 2 in 2018, and the headlines at the time said exactly that. Interstellar space, out of the solar system, free at last. The heliopause is not the edge of the solar system. It is not the edge of anything gravitational. It is the place where the solar wind, the stream of charged particles blowing off the sun, finally loses its shoving match with the thin gas between the stars. It is a weather boundary, not a border. Gravity does not stop there. Gravity does not stop anywhere near there. So if crossing the heliopause is not leaving, the obvious question is where the actual edge is, and once you know that number, everything you have been told about these 5 spacecraft has to be re-examined. The ecliptic is only one plane among many, and each of the others has its own up, and none of them agree with each other. Start with the one closest to you. The Earth's rotational axis is tilted about 23.5 degrees to the plane of its orbit. That tilt is the reason there are seasons, and it is also the reason there is a North Star. Polaris happens to sit almost exactly along the extension of the axis, which is why it appears to hold still while the entire sky wheels around it through the night, and why sailors could steer by it for centuries. But the axis itself moves. It traces a slow circle in the sky, one full turn every 25,770 years or so, wobbling the way a spinning top wobbles as it slows. Polaris has not always been the pole star, and will not remain one. In about 12,000 years, the bright star Vega will be near enough to the pole to serve, and for long stretches of that cycle, there is no bright star anywhere near the celestial pole at all. Thousands of years in which the sky has no fixed point in it, and anyone navigating by the stars has to manage without. Now go one step out. The moon's orbit around the Earth is tilted about 5 degrees to the ecliptic. 5 degrees is almost nothing, and it is the reason you do not see a solar eclipse every month. Think about how strange that is. Every 29.5 days the moon passes between the Earth and the Sun. On the face of it, there should be an eclipse each time. There is not, because that 5-degree tilt means the moon usually passes slightly above or slightly below the Sun in our sky, rather than in front of it, and misses. Only twice in each orbit does the moon's path actually cross the plane of the ecliptic, at 2 points called the nodes. An eclipse can only happen when a new or full moon coincides with the moon being at one of those 2 crossings. That produces eclipse seasons roughly every 173 days, and the famous Saros cycle of 18 years, 11 days and 8 hours, after which the whole geometry very nearly repeats. 5 degrees of misalignment turns a monthly event into a rare one. Those 2 crossing points do not stay put either. They slide slowly backwards around the ecliptic, completing a full circuit once every 18.6 years, which sets the long rhythm of when eclipse seasons fall and how far north and south the moon rises through the year. Some prehistoric monuments appear to be aligned to the extremes of that cycle, which means people were tracking the intersection of 2 orbital planes, by eye, thousands of years before anyone knew there were planes to intersect. Go further out and Saturn shows you the same principle written large. Saturn's rings lie in the plane of Saturn's own equator, which is tilted about 27 degrees to Saturn's orbit around the Sun. Saturn takes about 29.5 years to go around, and over that time the angle at which we see the rings changes continuously. For years at a stretch they are wide open and spectacular. Then they narrow, and then, roughly every 15 years, they turn exactly edge onto us and effectively vanish. A structure 280,000 kilometers across, disappearing from all but the largest telescopes, because it is so thin that seen along its own plane there is almost nothing there to see. It happened most recently on the 23rd of March, 2025. It will happen again around 2038. There is one apparent counterexample to everything in this video, and it deserves to be answered honestly rather than ignored, because it looks decisive. Satellites fly polar orbits all the time. Weather satellites, imaging satellites, mapping satellites. Enormous numbers of them travel from pole to pole over the Earth while the planet rotates underneath, which lets them scan the entire surface strip by strip. If perpendicular orbits are so ruinously expensive, how is this routine? The answer is that those satellites were never turned into polar orbits. They were launched directly into them, from sites chosen for exactly that purpose, and they never had a different plane to leave. Changing an existing low Earth orbit from equatorial to polar after the fact would cost somewhere around 8 kilometers per second, roughly as much as it cost to reach orbit in the first place. Nobody does it. It is not done because it cannot be afforded exactly as everywhere else. Polar launches even give up the small free boost from the Earth's rotation, and mission planners accept that penalty rather than face the alternative. The International Space Station orbits at an inclination of 51.5 degrees, and that number is not aerodynamic or scientific. It is diplomatic. It was chosen so that launch sites in both the United States and Kazakhstan could reach it efficiently, because neither partner could afford to change plane once in orbit. Even in the friendliest possible engineering environment, a few hundred kilometers above your own planet, the rule holds: choose your plane before you leave the ground, because afterwards you almost certainly cannot pay for a different one. Now go all the way out. Our galaxy is itself a flattened rotating disk, and it is flat for exactly the same reasons the solar system is. An enormous cloud of gas that collapsed, conserved its rotation, and had its vertical motion cancelled by countless internal collisions on a scale of hundreds of billions of stars rather than 8 planets. When you look at the band of the Milky Way stretching across a dark sky, you are doing precisely what the ancient sky watchers did with the zodiac. One level up, looking edge-on at a flat disk from a vantage point inside it. The galaxy is thicker, relatively speaking, than the solar system is. Its stellar disk is about 100,000 light-years across and something like 1,000 light-years thick where we are, a ratio of about 100 to 1 rather than the 30 to 1 of the planetary system. But the physics is identical, and so is the consequence. Almost every star you can see with the naked eye is riding in that layer, going the same way, for the same reason the planets are. And the ecliptic is tilted about 60 degrees to the plane of that galaxy. 60 degrees. The up of our solar system and the up of our galaxy are almost at right angles to each other. They are not related. They were never related. Two rotating systems that formed independently, billions of years apart, one nested inside the other, each with its own inherited spin, each with its own perpendicular direction, and no reason on Earth or off it for them to agree. The Sun sits about 26,000 light-years from the centre of the galaxy, and takes roughly 230 million years to complete one orbit, a span so long that the last time we were in this part of the galaxy, the earliest dinosaurs had not yet appeared. And within that orbit the Sun also bobs gently up and down through the galactic plane, pulled back each time it strays too far by the combined gravity of the disk, crossing the midplane roughly every 30 million years, carried a few hundred light-years above and then a few hundred below. We are at this moment moving up or down relative to our galaxy, just slowly enough that nothing in the whole of human history has noticed. Some researchers have asked whether those crossings correlate with mass extinctions or impact rates on Earth. The idea is reasonable and the evidence is contested. It is worth mentioning and not worth believing yet. Go further still, and the concept dissolves entirely. Our galaxy belongs to the local group, a few dozen galaxies bound together. The local group belongs to Laniakea, a supercluster of roughly 100,000 galaxies spanning more than 500 million light-years, mapped only in the last decade or so by tracing how galaxies flow toward a common gravitational focus. And Laniakea is one node in the cosmic web, filaments of galaxies and dark matter stretching across hundreds of millions of light-years, connected at dense knots, separated by nearly empty voids. At that scale there is no disk to be perpendicular to, there is no dominant rotation, there is no up. The evidence for that is direct. The cosmic microwave background, the oldest light there is, has been measured across the whole sky, and it is the same in every direction to about 1 part in 100,000. There is one larger variation, about 1 part in 1,000, and it is not cosmological at all. It is our own motion, at roughly 370 kilometers per second, showing up as a Doppler shift. Subtract ourselves and the universe is uniform. Every up is borrowed. It was true of your inner ear in the first minute of tonight, when 3 biological systems stopped agreeing with each other in free fall. It is true of the plane you're riding at 29.8 kilometers per second. It is true of the galaxy's disk, tilted 60 degrees to ours for no reason at all, and it is true all the way out to the point where there is nothing large enough left to lend you a direction. Every up in this universe was on loan from something nearby, and every single one of them has to be paid for, except, it turns out, for the ones that do not. On the 19th of October 2017, a survey telescope in Hawaii picked up a faint moving object that was doing something no known object in the solar system does. It was not on an ellipse. Its path was open, a hyperbola, a curve that comes in once and leaves and never returns. And it was coming down through the plane of the solar system at an angle of about 123 degrees, which is to say steeply and backwards. It was given the name Oumuamua, and it was the first object ever confirmed to have come from outside our solar system. It fell in, whipped around the sun, and left, and it is gone permanently, and it did not spend a gram of anything to do it. Oumuamua was strange in other ways, and it is worth being straight about them. It appeared to be elongated, possibly several times longer than it was wide, tumbling rather than rotating cleanly. It showed no visible tail or dust coma, which is unusual for something that close to the Sun, and as it departed it accelerated very slightly more than gravity alone could explain. That last detail launched a great deal of speculation, including a widely publicized argument from the Harvard astronomer Avi Loeb that it might be an artifact rather than a rock. The mainstream explanations are considerably more ordinary: outgassing of material too fine to see, or a body rich in frozen hydrogen or nitrogen quietly boiling off, and they account for the acceleration without needing anything exotic. It is a genuinely odd object, and it left before anyone could look properly, which is a frustrating combination. 2 years later, in August of 2019, an amateur astronomer in Crimea found a second one, a comet this time, clearly outgassing, on an equally open path inclined about 44 degrees. It was named Borisov. Then, in July of 2025, a third arrived, found by a survey in Chile and designated 3I/Atlas, on a steeply backwards trajectory tilted close to 175 degrees, which means it was travelling almost exactly opposite to the direction everything else in the solar system moves. 3 visitors, 3 completely different angles, none of them anywhere near the plane, and that is the point. Objects from outside arrive from every direction without preference, because they were never part of our disk. They never inherited our motion. They owe the plane nothing, and it has no hold on them. Finding 3 of them within 8 years tells you something about how many must be out there. Every young star system, in the process of building planets, flings enormous quantities of leftover material out into the galaxy. The same gravitational scattering that produced our own outer shell of icy bodies, operating everywhere for billions of years. The estimates run into the trillions of ejected objects per star. The space between the stars is not empty. It is thinly littered with the debris of planet formation, drifting on paths that belong to no system at all, and our surveys have only recently become sensitive enough to catch one as it goes by. The same logic explains something much older. Long-period comets, the ones that appear once and are not seen again for tens of thousands of years, arrive from every part of the sky, rather than clustering near the ecliptic the way short-period comets do. Jan Oort noticed this in 1950 and drew the correct conclusion. They must come from a roughly spherical shell of icy bodies surrounding the entire solar system, far beyond the planets, with no preferred plane at all. That shell has never been directly observed. Its existence rests almost entirely on the fact that comets fall in from everywhere. So out there, at the very edge of the Sun's territory, up finally stops meaning anything, not because the direction becomes impossible, but because the material stops caring. Approach that region from directly above the ecliptic, from directly below it, or from anywhere along it, and you would find much the same thing. Then, in April of 2025, a result appeared that is stranger still. A team led by Thomas Baycroft at the University of Birmingham had been using an instrument on the Very Large Telescope in Chile to refine measurements of a pair of brown dwarfs about 120 light-years away, objects too large to be planets and too small to sustain the fusion that makes a star, orbiting each other closely enough that each one periodically passes in front of the other as seen from Earth. They were not looking for a planet. They found small, unexplained wobbles in the pair's motion that the 2 objects could not produce on their own. After eliminating every simpler explanation, one scenario survived: a third body, a gas giant, orbiting both of them, and not in their plane, nearly perpendicular to it, tracing a steep polar path over the top and under the bottom of the 2 brown dwarfs rather than riding around with them. If it holds up, and some researchers have raised reasonable questions about whether the detection is secure, it would be the first planet ever found on a genuinely perpendicular orbit around a pair of stars. Theorists had predicted such orbits could exist and be stable. Simulations show that a misaligned disk around an eccentric pair can be driven into polar alignment rather than settling flat, but nobody had seen one. Sit with what that means alongside everything else tonight. Somewhere about 120 light-years from here, an entire planet appears to be doing permanently, stably, and at no cost whatsoever the exact thing that consumed the single most expensive maneuver in the history of human spaceflight. Ulysses spent 16 months, an entire mission architecture, and a favour from the largest planet in this solar system to reach 80 degrees for a few months at a time. That planet has 90 degrees, all the time, forever, and it did not earn it. It formed in it. The impossibility we have been circling all night is not in the physics. The physics allows it everywhere. The impossibility is in where we happen to have started. There is one more way to get an up, and it is the only one human beings have ever been able to manufacture for themselves. If you cannot travel to a direction, you can build a force. Spin a structure around a central axis and everything inside it is pressed outward against the rim, and that outward push, technically not gravity at all, but indistinguishable from it to a body that only has 3 sensors and no way to tell the difference, becomes a perfectly serviceable down. Down is outward, away from the axis. Up is inward, toward the centre, where the sensation fades to nothing because the centre is barely moving at all. The idea is a century old. In 1929, a Slovenian engineer named Herman Potočnik, writing under the name Herman Nordung, published a design for a wheel-shaped space station spinning to produce weight along its rim, decades before any nation could put anything into orbit at all. In 1952, Werner von Braun popularized a similar wheel about 75 meters across in a series of widely read magazine articles, and that silhouette lodged itself so firmly in the public imagination that science fiction has been drawing it ever since. In the 1970s, the physicist Gerard O'Neill went much further, proposing rotating cylinders miles long, holding tens of thousands of people, with agriculture and weather and daylight brought in by mirrors. None of it has been built. Every station actually flown. Skylab Mir, the International Space Station, has been a non-rotating structure in permanent free fall because spinning a large structure safely is a far harder engineering problem than assembling a still one. The reason people keep returning to the idea anyway is that freefall does measurable harm over long periods. Bone density falls, muscle mass falls, fluids redistribute toward the head, which changes the shape of the eyeball and degrades vision in a way that does not always fully recover. Astronauts hold the losses back with hours of daily exercise, and it works well enough for 6-month stays. Nobody knows whether it works for 6 years. The obstacle to the large designs has never been the physics, which is simple, but the mass. An O'Neill cylinder would require millions of tons of structural material, and launching that from the Earth's surface is out of the question by several orders of magnitude. The proposals all assume it would be mined on the Moon, or from asteroids and assembled in place. That is a chain of capabilities nobody has yet built the first link of. The idea is not waiting on a discovery, it is waiting on an industry. There are limits to what spin can do, turn a habitat too fast or build it too small, and the difference in force between someone's head and their feet becomes noticeable and unpleasant, a gradient that makes people dizzy and sick. Build it large enough and turn it slowly enough, and the gradient becomes imperceptible, and you have manufactured a down that a human body cannot distinguish from the real thing. Life inside a rotating habitat would also be quietly, permanently peculiar in ways the drawings never show. Drop an object and it would not fall straight down, it would curve because you and the floor are turning underneath it. Climb a ladder toward the axis, and you would get lighter with every rung. Throw a ball in one direction, and it would behave differently from a ball thrown the other way. The manufactured down would feel entirely convincing while you stood still, and would give itself away the moment you moved, which tells you something worth carrying into the last part of tonight. Up does not require a planet. It requires a consistent force, pointing consistently, strong enough for your inner ear and your eyes and your feet to agree on. Planetary gravity is simply the most abundant and familiar source of that force. Rotation will do, anything steady will do. But manufacturing an up inside a spinning drum is not the same as being able to travel in one. You can build a floor anywhere in the universe. You still cannot choose a direction, and that is the difference the last part of tonight is going to turn on. Voyager 1 is about 170 times further from the Sun than the Earth is. It has been travelling for 49 years. It is the most distant object our species has ever produced, and there is no realistic prospect of anything overtaking it in your lifetime or your grandchildren's. Now here is the number that recontextualizes all of it. The Sun's gravitational territory does not end at the heliopause. It does not end at Neptune, or at the Kuiper Belt, or at any boundary any spacecraft has crossed. It ends at the outer edge of the Oort cloud, that spherical shell of icy bodies inferred from the arrival directions of long-period comets, which is estimated to lie somewhere between 100,000 and 200,000 times the Earth-Sun distance. Put differently, the region where the Sun's gravity dominates over the pull of the rest of the galaxy. Its Hill sphere, the honest edge of this solar system, has a radius of roughly 1 to 2 light-years. Voyager 1 is at 170. After 49 years at 17 kilometers per second, the fastest and furthest thing humanity has ever built has covered something in the region of 1 part in 1,000 of the distance to the edge of its own star's dominion. It will reach the inner boundary of the Oort cloud in about 300 years. It will take something like 30,000 years to pass through it. In roughly 40,000 years, it will drift within about 1.5 light-years of a small red dwarf called Gliese 445, which is currently in the northern sky in Camelopardalis, not because anyone aimed at it, but because it happens to be roughly in the way. On the 15th of November, 2026, Voyager 1 will reach a distance of about 25.9 billion kilometers from Earth. At that point, a radio signal traveling at the speed of light will take a full 24 hours to reach it. It will be the first object ever to be 1 light day away from us. Hold both halves of that at once. 49 years of continuous flight, 3/4 of a century of engineering and tracking and patience, and light crosses the whole distance in a day. And that entire journey is 1,000th of the way to the edge of the sun's grip. So did it leave? Technically, yes. Voyager 1 is moving faster than solar escape velocity. It is on an open path. Given enough time, it will never come back, and the same is true of its twin, of both Pioneers and of New Horizons. 5 objects have achieved escape velocity from the Sun. That is a real accomplishment, and it should not be taken from them, and notice what is still happening to it every second. Voyager 1 is not coasting freely through neutral space. The Sun is still pulling on it, and still slowing it down. It leaves the solar system the way a stone leaves your hand when you throw it upward hard enough to never come back. Rising the whole time, decelerating the whole time, never quite stopping. Its speed relative to the Sun has been dropping continuously for 49 years, and will keep dropping for tens of thousands more. It is a bound object's cousin, unbound by the narrowest of margins, still entirely inside the region its star governs, still being acted on by the same gravity that holds the Earth in place. The word interstellar in the headlines refers to the medium it is flying through, not to any relationship it has stopped having with the Sun. But look at how it happened, and at what the word escape is doing in that sentence. Not one of those 5 spacecraft chose the direction it is travelling in. Voyager 1 is climbing north at 35 degrees because a group of people in a room in 1980 wanted to look at Titan. Voyager 2 is descending south at 48 degrees because the only way to reach Triton was to pass close over Neptune's north pole. The Pioneers went where Jupiter and Saturn put them. New Horizons went where Jupiter put it. Every one of those headings was assigned, by a planet, by a launch window, by the geometry of the disk they were all born inside. Not a single gram of propellant has ever been spent by anybody to select a direction in space and then travel in it, and the direction that would represent a genuine choice, perpendicular, straight up out of the plane, the one heading that no planet can hand you and no encounter can arrange, costs about 42 kilometers per second, against about 12 to escape the solar system in the direction you are already going. That is the answer, and it is not what most people expect. It is not impossible to get out of the solar system. It is impossible to get out of it on purpose. The only exit available is the one you were already drifting toward at a speed you inherited, along a plane that was ironed flat by colliding dust grains, 4.5 billion years before anybody thought to ask about it. Escape, in the sense the word actually means, leaving on your own terms, in a direction you selected because you decided to, has never once happened, and with the propulsion any of us are likely to see, it is not going to. Everything we have ever launched is still doing what the disk told it to do. You are not on the disk, you are in it. That was true in the second part of tonight when it was only a geometric correction. It is a different sentence now. You are inside a structure that has never let anything choose, moving at a speed you cannot feel in a direction nobody selected, and the only way out that has ever been found is to go faster along the grain until the sun's grip gets thin, which takes, on current evidence, about 30,000 years. It is worth saying what that has cost us in a way that has nothing to do with fuel. Nobody has ever seen the solar system. Every image you have ever looked at of the planets arranged around the sun is a reconstruction, a drawing, a diagram, a model built from measurements taken from inside the layer, the way you might map a room you have only ever felt your way around in the dark. Ulysses got closer to the outside view than anything else and carried no camera. Solar Orbiter has a camera and got 17 degrees. The one photograph nobody has ever taken, and nobody currently alive is likely to see, is the ordinary one, the whole disk from above, in a single frame, the shape of the place we live. There is one small consolation buried in the Voyagers, and it fits the theme uncomfortably well. Both of them carry a record with no address on it, a message assembled by people who knew, with complete clarity, that the chance of anyone finding it is effectively zero, and who spent months arguing about which music to include anyway. It was launched in a direction nobody chose, on a trajectory determined by a moon and a launch window toward no one in particular, and it is still the most hopeful object ever built. There is something worth holding on to in that. We could not choose where to go, so we chose what to send instead. Let us put the whole shape of it together one last time before we finish. 4.5 billion years ago a cloud collapsed and its vertical motion was cancelled, collision by collision, and thrown away as heat. What was left was a flat disk, and everything in this solar system was built inside it, sharing its direction of travel. The Earth carries you around at 29.8 kilometers per second. Every spacecraft ever launched inherited that motion, and has spent its entire existence either using it or being defeated by it. Going with it is cheap. Turning 90 degrees away from it costs 3.5 times more than leaving the solar system entirely. One mission tried, borrowed a planet to do it, reached 80 degrees, and had no camera. 5 spacecraft are drifting outward on headings that planets chose for them, and the true perpendicular, the only direction that would represent a decision, has never been travelled by anything. Go outside some clear morning, an hour before the sun comes up. Get far enough from town that the sky's genuinely dark and let your eyes adjust for 20 minutes, which is longer than it sounds and worth doing properly. If the conditions are good, you will see a faint tilted column of light rising from the horizon where the sun is going to come up. It is soft, roughly triangular, dimmer than the Milky Way, and if you did not know to look for it, you would take it for the first hint of morning. Many cultures did exactly that, and called it the false dawn. It is not dawn. It is not starlight, and it is not the atmosphere. It is sunlight, reflecting off countless grains of dust, the debris of collisions between asteroids and the slow disintegration of comets, spread thinly through the inner solar system and concentrated, as everything is, in the plane. Astronomers call it zodiacal light, and it appears as a narrow tilted band for one reason only. You're looking at a flat sheet of dust edge-on from inside it. Stand in that light for a moment and understand what you're looking at. That faint column is the plane. It is the same structure that priced every mission humanity has ever flown, that sent Ulysses 16 months in the wrong direction to buy a favour from Jupiter, that decided which way Voyager 1 would leave, that makes the direction directly above your head the single most expensive destination in physics. It is not an abstraction in a textbook. It is visible, faintly, on any clear dark morning, to anyone patient enough to wait for their eyes. And if you turn away from it and look north, you will find Polaris, sitting almost exactly above the Earth's rotational axis, holding still while everything else turns. Earth's up came with a guide star. It is bright, it is easy to find, it has been used for navigation for centuries, and nearly every culture that ever looked up built stories around it. The solar system's up came with nothing. The north ecliptic pole, the true perpendicular, the direction we have spent tonight establishing that nothing can afford to travel in, sits in a dim part of the constellation Draco. There is no bright star there. There is no ancient name for it. No sailor ever steered by it. No mythology was built around it. No calendar was set by it. It is an unremarkable patch of sky that became meaningful only when astronomers worked out the geometry and calculated where the perpendicular pointed. Centuries after Polaris had already earned its place in every sky story on Earth. There is a pole in the sky with no star in it. That is what we could not reach, and it was never marked, because nothing has ever gone there. Every up is borrowed. Your body's up is on loan from a planet, arranged by 3 separate biological systems that were tuned for one specific condition and have no idea what to do without it. The solar system's up is on loan from a rotating cloud that flattened itself before the Earth existed. The galaxy's up is on loan from a much larger cloud that did the same thing, tilted 60 degrees to ours for no reason anybody will ever be able to explain. And past that there is nothing large enough left to lend you a direction, and the oldest light in the universe looks the same whichever way you point. None of that makes the up you woke with this morning less real. If anything, it makes it more remarkable. The floor beneath you exists because a cloud collapsed, and a disk flattened, and a planet condensed at the right distance, and a moon formed to hold its tilt steady, and all of it happened in an order specific enough that you can stand up in the dark without thinking about it. It is not a fact about the universe. It is a local arrangement, valid for exactly as long as you stay within reach of it, and it is the only one any of us has ever been able to afford. Sleep well.